In this video, we'll talk about the maximum and minimum values of a function. As an example, let's consider an object that's thrown straight upward from ground level with an initial velocity of 64 feet per second. The height in feet above the ground level after t seconds is approximately given by the formula s at t equals 64t minus 16t squared. A natural question to ask is, what is the maximum height the object achieves before falling to the ground? Since the graph of the position function, at least in this case, is part of a parabola, we can find the peak by identifying the vertex. So what we can do is we can rewrite the function, or at least the formula, by completing the square. And that's what we've done here. This is the formula once we've completed the square, and this enables us to very easily read off the vertex. The vertex is the point with coordinates 2, 64. The 2 comes from here, and the 64 comes from here. So that means that the maximum value is s equals 64 when t is equal to 2. So the maximum height that the object achieves is 64 feet, and it happens after 2 seconds. The value 64 is the largest value that s at t can attain on the interval from 0 to 4. We call it the absolute maximum value over the interval. Let's make this into a definition. Let f be a function with domain D. If c is a number in D, and f at c is greater than or equal to f at x for all x in D, then f at c is called the absolute maximum value of f on D. Basically, what this is telling us is that the output value for c is the largest possible value that the function can achieve. There might be other places that achieve the same value, but no other x value can give you anything larger. F at c is the largest possible value you can attain. That makes it the absolute maximum value, on some domain that you specify. We can also define an absolute minimum in the same way. Let f be a function on some domain D. If c is a number in D and f at c is less than or equal to f at x for all x in D, then f at c is called the absolute minimum value of f on D. Again, we're looking at some f at c value, which is an output, but this time we're saying it's the smallest possible value that f can achieve as an output. One important thing to understand about this is that this value is actually achieved. There is some input that gives you the output that is the smallest possible value that the function can achieve. That makes it an absolute minimum value of the function. As an example, consider the function f at x equals x minus 1 quantity squared plus 2. This is an upward opening parabola with vertex at 1, 2. So the absolute minimum value of f on the domain is y equals 2, which happens when x is equal to 1. The function that we're looking at here, f at x equals x minus 1 quantity squared plus 2, this has no absolute maximum value on the domain from negative infinity to infinity, because f at x increases without bound as x goes to infinity or x goes to minus infinity. You can see from the graph that there's a minimum value that occurs at this valley, but there's no maximum value because the function just keeps getting larger and larger and larger, increasing without bound. If we restrict the domain to a smaller interval, say from 0 to 3, in this case there will be an absolute maximum value on the restricted interval. We can imagine restricting our domain to the interval from 0 to 3. And then we're only looking at this smaller range of x values between 0 and 3. And that means as far as the graph is concerned, we're only looking at a small portion. We're only looking at this parabolic arc here. And you can see that on this parabolic arc, there actually is a maximum value that's achieved, which is right here. So this is the max value, or at least this is the point where there is a max value. So there's a max value at x equals 3. And we can even determine what that value is by plugging it into the function. When x equals 3, then y is equal to f evaluated at 3, which is 3 minus 1 quantity squared plus 2, which is 2 squared plus 2, which is 4 plus 2, which is 6. And that's believable from the graph. We can't always guess what a value is from looking at the graph because it might just be close, but in this case it's right. The maximum value that it achieves on this restricted domain is 6. The minimum is still the same. The minimum hasn't changed. It's 2 on this restricted domain. So even if a function doesn't have a maximum or a minimum on one domain, you might be able to look at a smaller domain and find a maximum or minimum value on that smaller domain. In the first example, we were looking at the function s at t equals 64t minus 16t squared. This is a downward opening parabola, or at least part of one. If the domain of the function was negative infinity to infinity, there would be no absolute minimum value, because then we'd have a parabola opening downward that decreases forever. But that's not the case here. S at t represents the height of an object above ground level while the object is in motion. So the object is in motion for the first 4 seconds, and that means that the domain is the interval from 0 to 4. And there is an absolute minimum value on this interval, and that minimum value is 0, which is when the object is on ground level. We're calling them absolute maximum or minimum values, but they go by many names. You can also call them global maximum or global minimum values. They're also known as extreme values. Collectively, we call them extreme values or extrema. And now I want to just draw your attention to something that you have to be careful about. When we talk about absolute maximum and minimum values, we're talking about the largest and smallest output values. That is, we're talking about the largest and smallest possible values for f at x. So we're talking about the y values when we talk about absolute maximum and absolute minimum values. We spend a lot of time looking for the x values, because once you have the x value, you can just plug it into your function and get the y value. But the actual values that you're looking for, the maximum and minimum values, those are output values. Those are the y values. But it's just often the case that it's easier to find the x values that give you those outputs, and then you just take those x values, plug them into the function, and get the output. This brings us to something called the Extreme Value Theorem. Well, this is the first part. The question is there any way to know if a function achieves a maximum value or a minimum value? Is there any way to know in advance? And sometimes there is. And the thing that tells us that is called the Extreme Value Theorem. It says that if f is continuous on a closed interval from a to b, then f does achieve its absolute maximum value and absolute minimum value somewhere on the interval. This is necessarily the case. If f is continuous on a closed interval, then f necessarily achieves its absolute maximum and absolute minimum values somewhere on that interval. So the function pictured here, for example, is continuous on a closed interval from a to b. Therefore, by the extreme value theorem, f does achieve an absolute maximum and absolute minimum value somewhere on the graph. Now, that doesn't necessarily tell you where it is. We can look on this graph and we can guess, oh, it looks like there's an absolute minimum value at this point, but we don't necessarily know what x value that is. And over here, on the left side, we can find a point that gives us a maximum value. But again, we don't know necessarily where that maximum value is happening at. We also can't tell for sure what the minimum and maximum values are. They look to be around negative 15 for the minimum and around positive 15 for the absolute maximum. But without knowing more about the function without actually having the formula, it's very difficult for us to tell what these actual output values are. One thing that you might notice is that the absolute maximum occurs at a peak, and the absolute minimum occurs at a valley. We'll explore a little bit more about that later. All we can say for certain right now is that since this function is continuous on a closed interval, then there is some place inside of that interval that gives you an absolute maximum, and some place inside that interval that gives you an absolute minimum value. It is not necessary for the interval to be closed and bounded in order to have extreme values. For example, look at the function f at x equals sine of x, pictured here, or at least portion of it is pictured here. This function has an absolute maximum value and an absolute minimum value on the infinite interval from minus infinity to infinity. This is not a bounded interval, it's infinitely wide. However, it does have a maximum value on this interval, namely 1, and it has a minimum value as well, which is -1. These both occur at many different x values, in fact, infinitely many. Notice that there's only one maximum value and only one minimum value. It might occur infinitely often, or just many times, but there can only be one absolute maximum and one absolute minimum. The absolute maximum is the largest possible value that it can attain, so it wouldn't make sense to say that there are two absolute maximum values, because an absolute maximum value is the largest possible value. There can only be one. It might happen at many different locations, but there can only be one maximum value, and there can only be one minimum value, or I should say absolute maximum and absolute minimum. While it isn't necessary for the interval to be closed and bounded, if it is unbounded, for example infinite, even a continuous function might not have a maximum or minimum value. For example, look at the function f at x equals the inverse tangent of x, or the arctangent as it's also known. This function is continuous on the interval from minus infinity to infinity. That means it's continuous everywhere. But it is always increasing. It never achieves an absolute maximum or an absolute minimum. It's always getting larger and larger, approaching pi over 2. So it wants to achieve pi over 2. If it had a maximum, it would be pi over 2, but it never actually gets there. Remember that in order to have an absolute maximum value, there must be some input that gives you that as an output. There is no input for this function that gives you an output of pi over 2. It's just always increasing, trying to get to pi over 2, but it never reaches it. For the same reason, there is no absolute minimum value. The function decreases as you move to the left, getting closer and closer to negative pi over 2. But there is no input that gives you negative pi over 2 as an output. In order to be an absolute minimum value, there must be an input that actually gives you the output, and there's not in this case. So this function has neither an absolute maximum value nor an absolute minimum value, at least not on the interval from minus infinity to infinity. On the other hand, even if you have an interval that's bounded, that is of finite length, if it's not a closed interval, then the function may fail to achieve a maximum or minimum value even if that function is continuous. For example, the function f at x equals tangent x. This is continuous on the interval from minus pi over 2 to positive pi over 2, not including the endpoints. But it has vertical asymptotes at the endpoints. In particular, the function isn't defined there. But the function is increasing without bound as x approaches pi over 2 from the left, and it decreases without bound as x approaches negative pi over 2 from the right. That means tangent of x never achieves a maximum or minimum value. Tangent of x can always get bigger, it's growing without bound. It can always get smaller, it's decreasing without bound. That means that there is no absolute maximum or absolute minimum on this interval from minus pi over 2 to pi over 2, even though the function is continuous there. That's because we're excluding the endpoints, and so there's room for it to grow further and further and further, or decrease further and further and further. Even if a function is discontinuous at some point on an interval that's closed and bounded, it might still achieve a maximum and a minimum value on that interval. For example, here we have a function that has a jump discontinuity at x equals 2. So it's not continuous on the interval from 0 to 4. It's continuous on most of it. It's just not continuous at x equals 2. And that means that the extreme value theorem doesn't tell us anything. The function is discontinuous. However, in this particular case, it still does achieve a maximum value and a minimum value on the interval. The absolute maximum happens at x equals 2, when y is equal to 10. It also has an absolute minimum value, which is y equals 2. The absolute minimum value occurs when x is equal to 4. Notice that the absolute maximum occurs at the point of discontinuity. The function is not continuous at x equals 2, but it's still defined at x equals 2. X equals 2 is still an input, and it gives you the largest possible output, which is 10. So there is an absolute maximum value of 10, and it happens when x is equal to 2. There's an absolute minimum value of 2, and it happens when x is equal to 4. So even though this function is discontinuous on a certain interval, it does have an absolute maximum and absolute minimum value there. However, a function that is discontinuous at some point on an interval might not achieve a maximum value or a minimum value on the interval. Consider the function here, for example. This is very similar to the previous one, it's just slightly redefined. For example, at x equals 2, there's still a jump discontinuity, but before the function was right continuous, now it's left continuous. And also, there's now a jump discontinuity at 4. The output when x is equal to 4 is no longer 2, it's something larger, probably 4, although it's hard to say for sure from the graph. This function, even though it's very similar to the previous function, has neither an absolute maximum nor an absolute minimum value. The absolute maximum you would think would be 10, except there's no input value that gives you 10. On the other hand, you can find input values giving you every value approaching 10, but never quite reaching 10. And it's for that reason that there's no absolute maximum value, because there's always some value which is just getting a little bit closer to 10, but never quite making it. Similarly, there's no absolute minimum value, because there's no value that actually gives you an output of 2. There's no input that gives you an output of 2. But you can find outputs that are getting closer and closer and closer to 2, decreasing to 2. So there's always another value which is a little bit smaller, closer to 2, but never quite making it. So it has neither an absolute maximum nor an absolute minimum value, and that's because of these jump discontinuities. The function f at x equals sine of x over x has a removable discontinuity at x equals 0. This function does not have an absolute maximum value on the interval from minus infinity to infinity, but it does have an absolute minimum value. In fact, you can see from the picture that it doesn't have an absolute maximum because the maximum should be 1, but there is no input value that actually achieves 1. The function is increasing on both sides of x equals 0, approaching the output of 1, but it never quite gets there. There's always some output which is just a little bit bigger or closer to 1, so there is no absolute maximum. But you can also see that it does look like there's an absolute minimum value, and it looks to happen at this point here and this point here. Sine of x over x is an even function, so it's symmetric about the y-axis. So if there's an x value that gives you an absolute minimum to the left of the y-axis, there will also be one to the right. And it looks like that here. Now, it's difficult to say what that value is or where it's happening at. Certainly, it's hard to do just by looking at this graph. So the question then becomes, is there some way to determine what the value is? Is there some way to determine what this absolute minimum value is? Let's look at another example. The function f at x equals x times e to the negative x. This function does not have an absolute minimum value on the interval from 0 to infinity if we don't include 0, but it does have an absolute minimum on the interval if we do include 0. So if the interval is open from 0 to infinity, we lose the minimum value. And you can see that there is a minimum value at 0. F at 0 is equal to 0. So we have a minimum value at this point. If you remove that point, if you remove x equals 0, then there is no absolute minimum value because the function decreases towards 0 from the left. It also decreases towards 0 as you move out towards infinity on the right, but it never actually achieves the output of 0 on the open interval from 0 to infinity. So that does not have an absolute minimum. It does have an absolute maximum, and we can see it's somewhere around this point. Now, it's difficult to tell what that absolute maximum value is. It looks like maybe it happens at 1, but it's hard to tell from the picture. So is there some way to determine what that maximum value is? In general, you can ask, how do you determine an absolute maximum or absolute minimum value of a function? The extreme value theorem tells you that if your function is continuous on a closed interval, then it will necessarily have an absolute maximum or absolute minimum. But it doesn't tell you, at least not yet, how to find them. So how do you determine the absolute minimum value of, for example, this function, x to the x, on the interval from 0 to 2? We can look at the picture and we can say, well, it looks like there is some minimum value, but what is it? Where is it? Is there some way to determine the location, that is the x value? Because then we could just plug it into x to the x, and that would tell us what the y value is. What about the function x to the cosine x that you see graphed here? This function appears to be continuous on the interval from 0 to 15. It looks like it does have a minimum value of 0, so we can pick that one out, but what about the maximum? It seems that there is a maximum, but it's hard to know what that value is. Is there some way to determine that value? And yes, there is. And once again, the extreme value theorem will come to our rescue. Now this is extreme value theorem part 2. So let f be a continuous function. Now it should just say let f be a continuous function on the interval from a to b. Then the absolute maximum value of f occurs at one of the endpoints of the interval or at a local maximum. The absolute minimum value of f occurs at one of the endpoints of the interval or at a local minimum. Well, what is a local maximum? What is a local minimum? A function f has a local maximum value at x equals c if f at c is the largest possible output value near to c. And similarly, f has a local minimum value at x equals c if f at c is the smallest output value for all x near to c. So that means you have a local maximum value if all of the other output values nearby are no bigger. You have a local minimum value if all of the values nearby give you something which is no smaller. But what exactly do we mean when we say near to c? When we say that f at c is greater than or equal to f at x for all x near to c, what we mean is that we can find some small open interval containing c, c is inside of it, such that f at c is greater than or equal to f at x for all x in that interval. So for example, in the graph that you see here, we have two local maximum values and two local minimum values. There's a local maximum at x equals a. So what that means is that if I draw a little interval around a, then on that interval, f at a is the absolute maximum, just on that small little interval. Similarly, for x equals b, we can find a small little interval so that on that interval, f at b is the absolute minimum, just on that small interval. And similarly with f at c and f at d, we can find small intervals so that f at c is the absolute maximum on that small interval, and f at d is the absolute minimum on that small interval. Let's look at C for a second. Now, it is a local maximum because I can find some small interval so that f at C is the absolute maximum on that small interval. But it's not the absolute maximum of the function over the entire domain, because there are plenty of places which are bigger. So if I just draw a horizontal line there, you can see that there are plenty of places where the function gives you output values that are bigger than f at C. So this gray dashed line happens at y equals f at C. And you can definitely see that there are output values that are bigger. And in fact, on the entire real line, this is a polynomial function, so on the entire real line, there is no absolute maximum or absolute minimum. But if you just look at some small interval, then f at C is the absolute maximum on that small interval. And similarly, f at B is the absolute minimum on some small interval. So this function has local maximums at x equals a and x equals c, and it has local minimums at x equals b and x equals d. For continuous functions, local minimum values occur at the bottom of valleys or dips on graphs, whereas local maximum values occur at the top of hills or peaks on those graphs. One thing that you might notice is that continuous functions have local maximum values or local minimum values at points on the graph where there is a horizontal tangent line or a vertical tangent line or no tangent line. And we can go back to our images and see that. If you go back to these images that have local minimum values, you can see that either there's a horizontal tangent line, that one for example, or perhaps a vertical tangent line, which you see here, or no tangent line. The absolute value function, which is what this is, has no tangent line at x equals 0. The pictures here for the local maximum case are just the reflections of the previous through a horizontal axis. So you have either a horizontal tangent line, a vertical tangent line, this is often called a cusp, or here you have no tangent line. This is typical for a continuous function. And in fact, we have a theorem to that effect. If f is a continuous function with a local maximum value or a local minimum value at x equals c, then either the derivative at c is equal to 0 or the derivative at c does not exist. This is often called Fermat's theorem. And it's a good way to help you discover if there are local maximum or local minimum values, because you can look at the derivative and ask yourself, is the derivative 0 there or does it not exist? This leads very naturally to a definition. If c is a number in the domain of f, for which either f prime of c is equal to 0, in which case it has a horizontal tangent line, or f prime of c does not exist, then it has either a vertical tangent line or no tangent line. In that case, we call c a critical number or a critical point for the function f. Consequently, from Fermat's theorem, we can say that local extreme values of f occur at critical numbers of f. Now, the critical numbers are the x values. The local extreme values are the y values. Now, not all critical numbers belong to local extreme values. So, for example, here we have the function f at x equals x cubed. This has a tangent line at x equals 0 that is horizontal. We can see that very quickly by differentiating. So f prime at x, just using the power rule, is 3x squared. So we can say that f prime of x is equal to 0 when x is equal to 0. So there is a horizontal tangent line at x equals 0, and it's just the x-axis. So we have a horizontal tangent line at x equals 0. But notice, so note, f at 0 equals 0 is not a local extreme value. If you look to the right of x equals 0, the function gets bigger. If you look to the left, the function gets smaller. So at no point on no interval is f at 0 a local extreme value. Remember, you have to be able to find a small open interval containing c. So in this case, c is equal to 0. So you have to find a small open interval containing 0 so that it's a local extreme value on that small interval. But in this case, that can't happen because as soon as you move to the right, you get something bigger, something positive, and as soon as you move to the left, you get something smaller, something negative. So there is no local extreme value at x equals 0, even though f prime of 0 is equal to 0. Basically what that means is that the function is getting very flat at x equals 0. And that also happened when you had a peak at a local maximum or a valley at a local minimum. You might have a horizontal tangent line there because the function gets kind of flat as it starts to change direction. You can think of this function as increasing and then it thinks about changing direction, but then it doesn't. Then it just keeps increasing. And that's why it's sort of flat there, and so there's a horizontal tangent line. But it doesn't give you a local extreme value. So this is important because you find local extreme values by looking for critical numbers, but not every critical number will give you an extreme value. They're your candidates for extreme values. Here's another case where a critical number doesn't belong to an extreme value, and it's very similar to the last one. If you look at the graph, you can see that you have a function which is always increasing. Now there is a very vertical point right here at x equals 0, and that's where you have a vertical tangent line. So the derivative won't exist there, because if you have a vertical tangent line, that means the slope is in some sense infinitely large. So the derivative won't exist there, and you can see that just by computing it. So f at x is equal to, let's rewrite it as x to the 1/3 so we can use the power rule. Then f prime at x is 1/3, x to the 1/3 minus 1 is a negative 2/3. So that's putting the x in the denominator. So it's 1 over 3x to the 2/3. So there is no place where this derivative is 0. However, f prime at x does not exist when x is equal to 0, because you have an infinite limit there as x approaches 0. So that means your derivative doesn't exist at x equals 0, and you can see that in the existence of this vertical tangent line. But also notice that this is not giving you an extreme value. F at 0 equals 0 is not a local extreme value. If you look to the right of x equals 0, so at x equals 0 you get 0, but if you look to the right, the function is larger, it's positive. If you look to the left, the function is smaller, it's negative. So here again we have a critical number that does not belong to a local extreme value. If you have a local extreme value, then it will belong to a critical number, but not all critical numbers will give you local extreme values. The critical numbers give you possible candidates for giving you local extreme values. They're just the candidate input values, but they might not all belong to local extreme values. Okay, so how do we find the absolute extreme values when f is a continuous function? Well, fortunately, there's a method to help us do that. So now we're going to detail the method for finding absolute extreme values when the function f is continuous. So suppose first that f is continuous on a closed and bounded interval from a to b. Now this is important because the extreme value theorem tells us that in a case like this, the absolute maximum value and the absolute minimum value both exist. Moreover, it tells us where they are. They're either at critical points or at the endpoints. So step 1, find all critical numbers of f in the interval from a to b. How do we do that? Well, we find all x in the domain of f. Now, it's important that we're in the domain of f. for which f prime of x is equal to 0 or doesn't exist. The case where f prime of x is equal to 0, that's the case where you have a horizontal tangent line. F prime of x not existing, that's the case where you either have a vertical tangent line or no tangent line. So you find all of the points in the domain where the derivative is 0 or doesn't exist. Let's just label these C1, C2, C3, and so on, however many there are. You can disregard any critical numbers outside of the interval. If it's not in the domain of f that you're considering, then it's not a critical number. Step 2, find the output values for the critical numbers. Just plug them back into the original function f. The extreme value theorem tells you that the extreme values exist and they're either at endpoints or at critical points. Now, these critical points might not necessarily give you the extreme values, but they're the candidates. So you take all of these critical numbers, C1, C2, C3, and so on, and just plug them back into the original function. Now, it's important that you plug them into the original function. If you plug them back into the derivative, you're just going to get 0 or does not exist, because remember, that's how you found them in the first place. You want to plug them back into the original function because you're trying to find the extreme values of f, not its derivative. That's step 2. Step 3 is to compute f at a and f at b. Those are the values of the function at the endpoints. Again, the extreme value theorem tells you that the extreme values are either at critical points or endpoints. So you just have to check the value of the function at each critical point and each endpoint. And then you just ask, well, which one's the largest and which one's the smallest? And that's step 4. The largest value you computed is the absolute maximum value, and the smallest is the absolute minimum value. And that's all there is to it. You're just looking for the extreme values, the largest and the smallest. And you know that they will happen, at least if f is continuous on a closed bounded interval. You know that those extreme values do happen, and moreover, they either happen at critical numbers or endpoints. So you just have to check the value of the function at all of the critical numbers and all of the endpoints and see which one's biggest and which one's smallest. Let's look at some examples. For our first example, we want to find the absolute maximum and absolute minimum values for this polynomial function. F at x equals x cubed plus 6x squared minus 15x on the interval from 0 to 2. This is a closed and bounded interval. The function is continuous, so we know that the absolute maximum and absolute minimum values do exist for this function on this interval. The first step is to compute the derivative. We want to find the critical points, so in order to do that, we need to find the derivative of f. So we just use the power rule on each one of these terms. So the derivative of x cubed is 3x squared plus 6 times the derivative of x squared, that's 6 times 2 is 12, x to the 1, then minus 15. This exists everywhere, so there are no cases where the derivative doesn't exist. So we just set this equal to 0, and then we solve for x. The first thing we can do is factor it. So we'll factor out a 3, and that will leave us with x squared plus 4x minus 5 is equal to 0. And we can continue to factor. This is 3 times x minus 1 times x plus 5, and set that equal to 0. Now this can only be equal to 0 if one of the factors is equal to 0, so either x equals 1 or x equals negative 5. So that means that we get the critical number x equals 1. We don't have to worry about x equals negative 5 because this one is not in the interval that we're considering. We're only looking at the interval from 0 to 2, so that means we only need to consider critical numbers that appear inside that interval. So negative 5 is outside of that interval, but x equals 1 is. So this is the only critical number, or critical point. All right, so step 2 is just to evaluate the function at all of the critical numbers. Well, we only need to worry about x equals 1. So we just look at f at x equals 1. That's going to give us 1 cubed plus 6 times 1 squared minus 15 times 1, which is 1 plus 6 minus 15, which is equal to negative 8. So that gives us one candidate value for an absolute extremum. We don't know if it is or isn't yet, but that's one of our candidates. All right, so let's just draw a vertical line here. So now step 3 is to check the endpoints. So we need to compute f at 0 and f at 2. F at 0 is quite straightforward. This is 0 cubed plus 6 times 0 squared minus 15 times 0, which of course is 0. So that's another candidate value. And finally, we need to check f at 2. So that's going to be 2 cubed, which is of course 8, plus 6 times 2 squared minus 15 times 2. So that's 8 plus 6 times 4 is 24, minus 15 times 2 is 30. And that will give us 2. Okay, that's our last possible candidate value. So now we just need to, for step 4, we just need to find the largest and smallest output value. Okay, the smallest is negative 8. So this one's the smallest, negative 8, and the largest is 2. So that tells us that the absolute maximum is the absolute maximum value is 2, and the absolute minimum value is negative 8. And 0 is neither. It's a candidate, but it just isn't. It isn't one of them. So the largest one is 2, that's the absolute maximum, and the smallest one is negative 8, so that's the absolute minimum. And that's our first example. Let's do another one. For our next example, let's find the extreme values for g at t equals the square root of t minus the square root of t cubed on the interval from 0 to 4. Now notice that we have a square root here and here. So this would be a problem if t could be negative, but it's not negative. We're only looking at the interval from 0 to 4. So this function is continuous on the interval from 0 to 4. So that means the extreme value theorem does apply here, and we know then that our extreme values do exist and are either at critical points or at the endpoints. Well, the endpoints are 0 and 4. Those are easy to find. What we need to do is find the critical points. So that's our step 1, find the critical numbers. And that basically means compute the derivative of g. So let's rewrite g as t to the 1/2 minus t to the 3/2. So that way it's written so that each term is t to a power. That makes it a little bit easier to compute the derivative because we can just use the power rule. So it's going to be 1/2 t to the negative 1/2 minus 3/2 t to the positive 1/2. Okay, that's our derivative. Actually, it might be helpful, at least conceptually, if we write this as 1 over 2 times the square root of t minus 3/2 times the square root of t. If we do it that way, we can see that there's a problem area when t is equal to 0, namely right here. This derivative does not exist when t is equal to 0. So that gives us a critical point right away. So we note g prime at t does not exist when t equals 0. So t equals 0 is a critical number. That's supposed to be number. There we go. So we've already found one critical number, when the derivative doesn't exist. We also need to see if there are any places where the derivative is equal to 0. So we want to check, is there any place where g prime of t is equal to 0? Well, g prime of t, let's write it down. It's 1 over 2 square roots of t minus 3 over 2 square roots of t. And we want to know if there's any place where that's equal to 0. So let's solve for t. So we're going to start by adding this term to both sides. So we'll have 1 over 2 square roots of t is equal to 3/2 square root of t. So now we can multiply both sides by the square root of t, and we'll have that 1/2 is equal to 3/2 times the square root of t quantity squared. So square root of t quantity squared, of course, is t. So that gives us 1/2 is equal to 3/2 times t. Okay, so let's continue on the right side. So we have that 1/2 is equal to 3/2 t. So if you multiply by 2 and divide by 3, you'll end up with 1/3 equals t. And this is your other critical number. So there are two altogether. So that's step 1. Step 2 is to evaluate the function at the critical numbers. So we have two critical numbers. The first one was t equals 0, and the second one was t equals 1/3. So we just need to compute g at 0 and g at 1/3. Well, g at 0 is quite straightforward. That's the square root of 0 minus the square root of 0 cubed, which is just 0. So this is one of our candidate values. The next one to check is g at 1/3. So that's going to give us the square root of 1/3 minus the square root of 1/3 quantity cubed. So that's the square root of 1/3 minus the square root of 1 over 27, which we can rewrite as 1 over the square root of 3 minus 1 over, well, 27 is 3 cubed. So that's 3 squared times 3, so that's 3 times the square root of 3. And if you give those a common denominator, you're going to need a 3 over 3 here. So that gives you 3 minus 1 is 2. So 2 over 3 square roots of 3. And that gives us another candidate value. Now, I don't know exactly what the value is of 2 over 3 square roots of 3, but I know that it's bigger than 0. So this is, so far, a candidate for the absolute maximum, and 0 is a candidate for the absolute minimum. But I don't know yet because there's still one point that I have to check. So for 3, we need to check the endpoints, but notice we've already checked one of the endpoints. There are two endpoints, 0 and 4, but g at 0 we've already computed. That, of course, was 0. So we already did this one. We already checked it. Because it was a critical number as well as an endpoint. But now we have to check the other endpoint, which is 4. So that's going to give us the square root of 4 minus the square root of 4 cubed, which is equal to 2 minus, well, the square root of 4 cubed is 2 cubed, which is 8. So that's going to give us negative 6. So that's another candidate. Okay, and certainly negative 6 is smaller than 0, which was our previous candidate for absolute minimum. So now we just pick the largest and smallest, and that gives us step 4. So the absolute max, at least on this interval, is 2 over 3 square roots of 3, and the absolute minimum is negative 6, at least on this interval from 0 to 4. Let's do just one more example. Find the extreme values of h at theta equals the square root of 2 times cosine of theta plus sine of theta quantity squared on the interval from 0 to 2 pi. Okay, so this one's going to be a little bit more involved because of the nature of sine and cosine. But let's just do it the same way. We start with step 1. Look for critical numbers. Now in order to do that, we're going to need to compute the derivative of h. So we need h prime of theta, which is, well, let's just write it out. The derivative with respect to theta of square root of 2 times cosine theta plus sine of theta quantity squared. And we want to differentiate that with respect to theta. Okay, so this is the square root of 2 times the derivative of cosine, which of course is a negative sine of theta, plus the derivative of sine squared using the chain rule. That's going to be 2 times sine of theta, and then we have to multiply by the derivative of sine of theta, which is cosine of theta. So this is h prime of theta. Now we need to find the places where this either doesn't exist or where it's equal to 0. Well, it exists everywhere. That's not a problem. The only thing that you have to do is you need to check where this is equal to 0. Now there are a lot of places where this is equal to 0 because of the periodicity of sine and cosine. However, we're only looking at this interval from 0 to 2 pi, and that's going to help limit the number of critical points that we have to check. Okay, so let's just go ahead and try and solve this for theta. And this is going to require a little bit of work. So the first thing that we're going to do is we're going to factor out the sine of thetas here. So we'll have that sine of theta times negative square root of 2 plus 2 cosine of theta is equal to 0. Now the only way this product can be equal to 0 is if one of the factors is 0. So you're going to have that either sine of theta is equal to 0, or the other option is that negative square root of 2 plus 2 cosine of theta is equal to 0. These are the two options. Now if sine of theta is equal to 0, that tells you immediately that either theta is equal to 0, theta is equal to pi, or theta is equal to 2 pi. Now there are of course many other thetas for which sine of theta is equal to 0, but remember we're just looking at the interval from 0 to 2 pi. So these are the only options on that interval. And notice we already have both endpoints, both 0 and 2 pi. Those are endpoints of the interval, and they're also critical numbers. So that's going to cut down a little bit on the work later. So that's for this equation, sine of theta equals 0. But we still have this equation right here. So we need to solve for cosine of theta first. So 2 times cosine of theta is equal to positive square root of 2, and now just divide it by 2. So cosine of theta equals the square root of 2 over 2. And there are a few places where this will happen. Well, there are in fact infinitely many, but once again we're only interested in this interval from 0 to 2 pi. And we can help figure out where these values are if we just draw a little unit circle. So I'll draw it in the upper right corner here, and let's put in some axes for this. There's a y-axis, and there's an x-axis, x and y. Now what we're interested in is we're interested in the places where cosine of theta is the square root of 2 over 2. So the first one of those is right here. That's pi over 4. And that's where they're both equal to the square root of 2 over 2. Now if cosine is equal to the square root of 2 over 2, that's the x value. So that means we're looking at this one. So in order to find the others, well, the other, we just drop down, we drop a perpendicular to the x-axis, and it intersects right here, and that gives us a square root of 2 over 2 comma minus square root of 2 over 2. But of course we're only interested in the x value, and so what angle is this? Well, one way to view this is the negative pi over 4, because you could think of this as negative pi over 4, but of course that's outside of our interval. What you have to do is you have to go all the way around. like so. You have to go all the way around. And so that makes it 7 pi over 4. So we see that we have two angles that we need to consider. So that gives us theta is equal to pi over 4, and theta is equal to 7 pi over 4. And these are the theta values that come from this equation. So you can see that we have a total of 5 critical numbers that we have to consider. So that takes us to step 2. So we just need to compute h at theta at all of these values. So h at 0 is going to be the square root of 2 times cosine of 0, which is, of course, cosine of 0 is 1, plus sine of 0 quantity squared. And that's, of course, that's going to be 0. Cosine of 0 is 1, so this is just the square root of 2. Okay, so we have a few more of these that we have to check. So we have h at pi, so that's going to be the square root of 2 times cosine of pi, plus sine of pi quantity squared. Now sine of pi, of course, is 0, and cosine of pi is negative 1, so we're going to end up with negative square root of 2 here. Now we have h at 2 pi, but that's actually going to be the same as h at 0 because of the periodicity. We can write it all out. Square root of 2 times cosine of 2 pi plus sine of 2 pi quantity squared, but sine of 2 pi is 0 and cosine of 2 pi is 1, so it's just the square root of 2. In addition to checking 3 of the critical numbers, we've also just checked the endpoints as well, because 0 and 2 pi, those are also the endpoints of our interval. Now we have 2 more critical numbers that we need to check. We need to check h at pi over 4 and h at 7 pi over 4. So this is going to be the square root of 2 times cosine of pi over 4 plus sine of pi over 4 quantity squared. And so this will be equal to the square root of 2 times cosine of pi over 4 is the square root of 2 over 2 plus, well, sine of pi over 4 is also square root of 2 over 2, so quantity squared. And of course those are these values here. So we already knew that those were square root of 2 over 2. And we can simplify these. Maybe we'll just go on to the next slide. So this will give us, let's just go over here. So h at pi over 4. So this square root of 2 right here times that square root of 2. Well, let's just write that as square root of 2 squared over 2. But of course that's going to simplify to 1 plus square root of 2 over 2 quantity squared. So that's going to give us 2 over 2 plus 2 over 4, which is 1 plus 1.5, or 3/2. And for the next one, we don't expect it to be much different. So we end up with square root of 2 times cosine of 7 pi over 4 plus sine of 7 pi over 4 squared. Cosine of 7 pi over 4 was square root of 2 over 2. And here we're going to end up with the opposite of square root of 2 over 2, but we're going to end up squaring it. So we're going to end up with square root of 2 times square root of 2 over 2 plus square root of 2 squared over 2 squared. And of course this is the same thing as before, so that's 3/2. So that gives us our other candidate. And I say candidate singular because notice that they're the same. So we only get one extra candidate here. So now for step 4, we just need to ask ourselves what's the largest and what's the smallest value. So we have square root of 2, negative square root of 2, positive square root of 2, and 3/2. Let's write these down. So the candidate values are square root of 2, comma, the opposite of the square root of 2, comma, 3/2. Now, we don't actually have to check any others, because if we write down step 3 here, we already checked the endpoints, because they were also critical numbers as well. So we don't have to do anything extra there. The only thing we have to do is pick the largest and the smallest. Well, it's easy to spot the smallest, that's negative square root of 2, and the largest is actually 3/2. 3/2 is 1.5, and square root of 2 is 1.4 something something something. So the largest one is 1.5. So that tells us that the absolute maximum on this interval is 3/2, and the absolute minimum is the only negative one, which is the opposite of square root of 2. And those are the extreme values for this function on the interval from 0 to 2 pi.